Section 3.10, Linear Approximations and Differentials. So what are we going to do here? The first part of this section is we're going to see how we can use linear functions to approximate other functions, maybe like cubic or quadratic functions. And when we say linear function, we talk about straight lines. And the most important thing here in approximation, in approximating functions, is to use the tangent line to approximate a given function at a given point or near a certain given point. So let's say we have this function f. I'm gonna draw a tangent line to this function at some point. Say that's the x-axis, a, so x equals a. So this point here has coordinates a comma f of a comma f of a. So we use tangent line to approximate functions. At a given point. So in this case, we're going to use the tangent line at a comma f of a as an approximation to the curve y equals f of x when x is near a, means near x equals a. Recall from before, the equation of the straight line is given by y minus y1 equals slope times x minus x1. And this point that we have, a comma f of a, this is x and y. So x1, y1. So y minus f of a equals, here we have x minus a. And we defined before the slope of the tangent line is the derivative of the function at x equals a. So we can put that in here. And if we solve for y, what we get, add f of a to both sides, plus f prime at a times x minus a. This is called the linearization of f at x equals a. That's called the linearization of f at x equals a. Now, let's see how we apply this to an example. Let's say they ask us to find the linearization of the function f of x equals the square root of x plus 8 at a equals 1, and use it to approximate the numbers, square root of 8.96 and square root of 9.05. So I'm going to use these to do some approximation. Well, they asked find the linearization. So to find the linearization using the box formula, we need a, f of a, and the derivative at a. So three things. A is given. How do I find f of a? Well, just substitute. F of 1 is the square root of 1 plus 8. That's 9. 3. That's f of a. Now we need to find the derivative of that function at that point. So let me rewrite this. How do I find the derivative of this function? We rewrite it as 1/2. Then f prime of x would be 1/2 down x plus 8 to the negative 1/2 by the chain rule times 1. And this can be rewritten as bringing that down like so. So then f prime at 1 is 1 over 2 square root of 1 plus 8. That's 1/6. That's f prime at a. So we found all of them, the three of them. Then we use y equals f of a plus f prime at a times x minus a. F of 1 plus the derivative at 1 times x minus 1. And then what we get here, f of 1 was 3. The derivative at 1 was 1/6, x minus 1. And then what we do is we really need to simplify this. Multiply the 1/6 out, minus 1/6. Then combine the 3 and the negative 1/6 by finding the common denominator, which is 6. That's 18 minus 1, 17 over 6. So this is called linearization of the function. So we can say the given function, which is the square root of x plus 8, is about or approximated by this function. The next part is asking us to use this, whatever we just got, to find the square root of 8.96. The square root of 8.96. How do we find this? Well, to do that, let's convert this to the given function. So I'm gonna look at this, see if I can compare it to this. That looks like I can rewrite this as 8 plus 0.96. And comparing both sides, I see that x is the same as 0.96. X is the same as 0.96. Remember how, so here x is 0.96. But I'm going to use the x plus 8 was approximated by 1/6x plus 17 over 6. Substitute that in. 0.96 plus 17 over 6. And then if we take the common denominator 6, that gives 0.96 plus 17, which is 17.96 over 6. And if we divide that out, which is not difficult to do so, we get about 2.99. So to test it out on the calculator, you can check it on the calculator. You will see that the calculator will give you a value that is really close to 2.99. How about the other one, the 9.05? Well, we compare it again to the given function, which is x plus 8. I'm going to compare this to this by rewriting. So we have 8 plus 1.05. 1.05. So this tells us that x is 1.05. So now I can use that function 1 over 6x plus 17 over 6. And that will give us 1.05 plus 17 over 6. And this is in return 18.05 over 6. If we divide that out, that gives us about 3.01. So that's differentials, like how we use linear approximations, like specifically tangent lines, to approximate functions. And notice how I was able to find the square root of 8.96 and 9.05, which is interesting, using calculus to find the values of these two radicals, which can be difficult to find by hand if we don't use calculus. Now, the second part of this section is called differentials. Differentials. What are differentials? We know that y prime, or written as f prime, can be written using Leibniz notation, dy dx. From here, we can define dy as the derivative of the function as times dx. That's what dy. So if we say if a function f is differentiable, then the differential the differential dx is an independent variable, and the differential dy is the dependent variable. These are the two variables or two differentials. So dx is a differential and dy is also another differential. Not difficult to use, and now I'll show you examples first. Find the differential dy here for each function. So let's look at the first one. Y equals x squared times cosine 3x. So to do so, we defined, remember, the differential dy as f prime of x times dx. So f prime, basically the derivative of that function, which is x squared times cosine 3x times the derivative times dx. How do I find the derivative of this one? It's a multiplied. We use the product rule, which says the derivative of the first function, 2x times the second one, plus the derivative of keep the first one the same, derivative of the other one, negative 3 sine 3x. All that dx. And this can be rewritten as 2x cosine 3x minus 3x squared sine 3x, all of that dx. That's the differential. Look at another example. Y equals x squared over x minus 1. X squared over x minus 1. So how do you find the differential? Dy, again, is the derivative of this function times dx. How do you find the derivative of this function? We use quotient rule. Quotient rule says we take the denominator times the derivative of the top, derivative of the denominator times the top, divided by the denominator square. Dy equals, this is 2x, this is 1 times x squared, x minus 1 squared. So now, all we have to do is just simplify. We keep the denominator the same. We distribute this. 2x squared minus 2x minus x squared divided by x minus 1 squared times dx. Simplify the top one by combining like terms. That gives us x squared minus 2x over x minus 1 squared dx. That's dy. Those are called differentials. So where do we use those differentials? Back to the linear approximation that which we started with the lesson here today. So I'm gonna draw like any random function like so, and a tangent line. Let me make it more. So let's say that's a tangent line, and call this point P here at x. Okay, at x. If I move delta x this way, that becomes x plus delta x. And we're going to project it up to touch the graph at q of x. So there are 2 points. P is, this function is f, x comma f of x, and q is x plus delta x comma f of x plus delta x. These 2 points. And then we're gonna move this up, extend it to a point, call it R, where the vertical line is gonna touch the horizontal line. This is the tangent line, or let's call it the linear approximation. That's the linear approximation. So what we have next here, this distance is delta x. This distance is delta x. Where is delta y? Well, let's project this up this way. That's 90 degrees. That's delta x. This is delta x. This distance, I'm going to label here in green. This is delta y. Delta y. So if I want to find delta y, what is delta y? Notice this distance is f of x. This distance from let me do a different color, from here to here, that's f of x plus delta x. That's the y value, the vertical y value. So if I take that f of x plus delta x, the distance, the vertical distance, and subtract f of x, because this distance from here to f of x, which is the same as this. So if I subtract f of x from that one, that gives me delta y. That gives me delta y. And so what is this basically? This is the change in y. That's the change in y. Delta y. Now, the next thing students ask, what this has to do, what's delta x here? We are going to look at what we started with earlier when we started with small d of x and small dy. If you remember, dy and dx. We didn't do delta x and delta y. We just started with dy, dx. Now, what is delta y, dy and dx here? So in a different color, I'm going to label this. The distance from here to here, that's our dy. And this one is dx. So dx is approximately the same, or you can say almost the same as delta x. So dx and delta x are almost the same. These are the same. So how are we gonna get to work on this? First thing, note, as delta x gets smaller, then dy becomes almost the same as delta y. So in other words, if let's say we fix point P there on the graph, and we move point R toward point P, that vertical distance, dy, is going to get smaller and smaller, and then delta y will get smaller and smaller at the same time. So they will get really close to each other, And to see how to apply this to an actual example, let's take, as an example, let's compare values of delta y and dy. See how close they can be if the function f of x defined by x cubed minus x squared plus 3x minus 1, and it's given, and x changes from 2 to 2.06. So x moves from 2 to 2.6. So if I put that on the number line, what does that mean x changes? So say x is here, and this is x plus delta x is 2.06. So the distance from here to here, that's delta x, which is 0.06. That's what we have. Now to find delta y or to compare delta y and dy, we need to find each one of them. Remember, we defined dy to be f prime of x dx. So what's f prime? F prime is 3x squared minus 2x plus 3 dx. That's what the dy is. Now, we know what x is. X is 2. So we're going to substitute that in. 3 times 2 squared minus 2 times 2 plus 3 dx. Wait, what's dx here? Remember, we said dx is the same as delta x. So you can substitute right away dx or using 0.06. That gives us dy. If we calculate everything in, that's 4 times 3, 12, minus 4, 8, plus 311 times 0.06, that's 0.66. That's dy. And what is delta y? We define delta y as x, f of x plus delta x minus f of x. So delta y is f of x is 2 plus 0.06 minus f of 2. So this means I need to find f of 2.06 by substituting that in and minus f of 2. If we put that into the given function, we get delta y about 0.6782 to 4 decimal places. That's what we get. Notice if you convert these two values, notice how close they are. So as I decrease the value of delta x, as we decrease it, you know, where it says from 2 to 2.06. If this was like from 2 to 2.0006, for example, then these two boxed values will get really closer to each other, more than what you see now on the screen. We can take a look at another example. Compute delta y and dy for the given value of x, and it's given, to remind you, dx and delta x are the same. So the function is 4x minus x squared, x1, and they give us delta x, negative 0.3. So let's see how that works here. Again, I need to find dy. dy is f prime of x dx. dy equals derivative of the function 4 minus 2x dx. At x equals 1, that becomes 4 minus 2, and dx is delta x, which is negative 0.3. Calculating this, 2 times that is negative 0.6. I got dy. What about delta y? Delta y is f of x plus delta x minus the function. This is 1 minus 0.3 minus f of 1. That becomes f of 0.7 minus f of 1. If you substitute that into the function, you get negative 0.69. Very close to each other. Now, where do we use these things? Well, first thing, we introduce the error. Error can be the error in the area, dA in volumes, dV in surface area, dSA, and so on and so forth. We introduce relative error. Relative error is the error divided by the total. Error divided by the total, which is dA over the area, or dV over the volume, or so on and so forth. And the last one is percentage relative error. And what is that? This is basically relative error that we found in the previous line times 100%. So it's basically converting the relative error into percentage. How do we apply this? Let's say the radius of a circular disc is given by R equals 24 cm with a maximum possible error in measurement of 0.2 cm. Part A, use differentials. To estimate the maximum error in the calculated area. In the calculated area. Well, they ask us about dA. That's what the error in the area. Where A is the area of the circular disk. It's circle, so the area of the circle, we know it's pi r square. We are going to differentiate both sides. So dA 2 pi r dr. So what they give us here, they give us the radius, which is 24, and they give us dr, which is 0.2. If you read, it says with a maximum possible error in the measurement, that's the maximum possible error in the measurement of the radius, which is 0.2 centimeters. And then if we multiply all of this, it gives us about 30.159. Let's add another part to this, part B. What is the relative error? There are several ways to do this. Either you start with the formula. You know how we have dA, we found it earlier, 2 pi r dr. And we need dA over A. So we can divide both sides by A. A is the area. So then dA over A, what's the area? The formula for the area, it's pi r square. So the area, pi cancels out, r cancels out. So dA over A is 2dr over r. 2dr over r. And notice we already have both of them. We have dr 0.2 and the radius was 24. Dividing this up, it should give us 0.01667. What about if we add one more part to this? Let's ask about what is the percentage relative error in the area. In the area means the area of the circular disk. So all we have to do is take the relative error that we just found times 100%. So what was this? 0.01667 from the previous part times 100%. When you multiply by 100, that moves the decimal point to the right side 2 steps, becomes 1.667%. That would be the percentage relative error. So when we are when they ask about find dA, that's called differential. And what this tells us, this basically approximates the error in the calculated area of this disk. And this can be applied to volumes, surface areas, any other geometric shapes related to areas, volumes, surface areas. And it has also other applications in physics and chemistry. But these are the ones that we use here in this section most of the time. Is how you find, as a quick review, how we use, or we are given a function. We can use tangent lines to approximate those functions at a given point. If we have no access to something that we cannot find, so linear approximations kicks in to help us to do so without using calculators. And we saw some applications in this example, how we could use the square root of decimal numbers without using calculators. And then we introduced differentials. Those differentials, dy and dx, one of them is dependent, one is independent, because we call them dependent and independent because dy, the differential dy, depends on dx. That's why it's called dependent variable. So whatever value of dx you have, it's used to find dy. That's why dependent. but dx is independent of dy. And then we looked at a couple examples here, or 3 examples, or 2, yeah. And then we tried to show you geometrically what is dy and dx here by introducing more variables like dx, delta x and delta y. And then what happens is we try to show you as we make delta x smaller and smaller, the linear approximation gets closer and closer in value to the actual value. That's what this figure is about. But we in mathematics, we say, approximating something better than not knowing how to do anything with it. And then we looked at dy and delta y, and then we just made sure we started with an x equals 2 and delta x is 0.06. And we noticed how these two values, dy and delta y, were very close in value. And then the same thing can be applied to that example. And then we applied to other examples from real life situation, let's say, or something related to geometry, about the estimations in the possible area of a circular disk. So a circular disk is just a circle that is filled up. So we call it disk. So we use differentials that we just learned earlier to find the estimated maximum error in the area of the circular disk. And then from there, we get the relative error and the percentage error. This is what this section is about.